Okay, now I'm recording. Thank goodness I remembered. All right, so yes, if it compounds weekly, n is 52, which means for my formula I have a is equal to 1 times 1 plus 1 over 52 to the 52 times 1 power, which should equal 53 over 52 to the 52nd power, okay? Which is approximately what value? Come on, guys, I want you guys to tell me.
2.69259695.
Yes, about 2.69259695. Okay? So you notice that immediately, like when we first started doing this, right, the number of n, or the number of times it compounded really made a huge impact on the increase in value. But you'll notice we're starting to slow down a little bit, right? So what about daily? What would be my n for daily? What would be the number of times it compounds in a year daily?
365.
All right, 365, which again, my formula, a is equal to 1 times 1 plus 1 over 365 to the 365 times 1 power, which is equal to 366 over 365 to the 365th power. You guys see the pattern, right? Okay. Which is give me about how much?
2.7145674482.
Hold on, 2.7145674482. Yes. Okay, yes. Right? So again, we're still slowing down. What about hourly? What is the number of times it compounds in a year if it compounds hourly?
8,760.
Perfect. 8,760. Okay? So again, applying my formula, A is equal to 1 times 1 plus 1 over 8760 to the 87/60th power, or times 1 power, times 1 power, which would give me 8761 over 8760 to the 87/60th power, which is approximately what? 692, okay. Perfect. Okay. So obviously we're kind of reaching a peak point here, as I just jumped up from my number of compounds from 365 to 8,760, right? Yet the amount that my money's gone up has only been what? Not even a cent. Fractions of a cent in an entire year. Okay? So we're really slowing down at this point. So now let's see what happens if it compounds every minute. So how many minutes are in a year? 525,600 minutes. Okay? In a year. So that means this thing is compounding 525,600 times. And let's see how much that made our value go up. Plus 1 over 525,600 to the 525,600 power, which is equal to 525,601 over 525,600 to the 525,600 power, which is approximately what? 2.718,279,243. Okay? And now our last one. If this thing compounded every second, how many times would it compound in a year?
31,500.
Like 31,000? Oh no.
31,536,000.
31,536,000, correct? Okay. So now we have this thing that compounds over 31 million times in a year. And let's just see how little essentially our value goes up. 1 times 1 plus 1 over 31, 5, 3, 6, 0, 0, 0 to the 31, 5, 3, 6, 0, 0, 0 power, which is equal to 31, 5, 3, 6, 0, 0, 1 over 31, 5, 3, 6, 0, 0, 0 to the 31, 5, 3, 6, 0, 0, 0 power, which gives us approximately how much? Perfect. 2.718281778. Okay. So you can see that we basically kind of reached a pinnacle number here. So what happened as n increased? Well, as n increased, my amount increased, right? Every single time, no matter what, my amount increased. Okay. Now, it's kind of weird because it skyrocketed at first and then really, really slowed down. But so as n increased, the amount increased, but tailored off at higher values of n. Okay. Did the amount change at a constant rate? Absolutely not. Not even close. Okay. In fact, it was kind of like backwards exponential. Like it started a lot and then got really, really, really tiny. Okay. Is there a limit to how big the amount can get? And if so, what is it? You guys think there's a limit? There actually is. Okay? There's actually a limit. And that limit is our value E. Okay? E, which is approximately 2.71828 1828. Okay? And it is, believe it or not, it is a constant value. Now, it's a constant, yet it's also irrational. It's very much like pi. That's why we use the letter E to kind of denote it. Okay? So again, it's a constant value. It doesn't change, right? But it's irrational. Now, luckily we live in the times where our calculators almost all have E on them. Can you shut that door? Our calculators almost all have E on there, so we don't have to worry about kind of typing it in approximating it. But if you are using a calculator that doesn't have the E value, right, then if you're going to type it in your calculator, you're going to use what I call approximate E, okay, which is 2.71828, okay? So you should never do less than that if you're typing in E onto your calculator, okay? So why this value is important and where we mostly use it is, again, you can see that the more values of n, the closer and closer it gets to this number, okay? So we're actually going to now assume that we're compounding all of the time, because that's what compounding essentially continuous is, and that's kind of what value we determined if I keep going higher orders of n, like Jaden said, milliseconds, right? We might, right? We're gonna obviously get closer and closer to that value. So now pull out the next sheet. Sorry, I hit done. I hit that, which is up here somewhere. Yeah. The fill in note 7.2. And we're going to show you where we see it. Again, we're only going to do examples 1 and 2. You do not have to do the you do part. Okay? Because we already did that the other day. You don't have to, oh, I should not have done that. Right, you do not have to do this stuff. Okay? So, continuously compound interest formula. Okay? So if I deposit into, so again, for the most part, if you're depositing into a savings account, you're most likely going to have like a compounding, like semi-annually or annually. You're going to have something that doesn't use necessarily the continuously compounded interest formula, right? But if you're taking out a loan, most of the time you do, okay? Most of the time the banks will use a continuous compounded for loans, but not for if you deposit in their savings account, which is kind of backwards if you ask me, okay? So, the continuously compounded interest formula is A, my amount, is equal to my principal times E to the rate times time, okay? Or PERT, okay? You want to remember your continuously compounded interest formula, just PERT. Use PERT. Not PERT plus, it's PERT. Okay, that was a terrible joke. Anyway.
Very funny. I have no idea what that means, but.
Okay, so for our formula, we have 3 key parts. Okay, so P, which is our principal, R, which is our rate, and time, or T, which is our time, and again, I can't stress this enough, in years. Okay? It has to be in years. So let's look at one example of how we use this and where this works. Okay? So, suppose you invest $2,000 at an annual interest rate of 5.5% compounded continuously. Okay? How much will you have in the account in 10 years? Okay? So, let's talk about what we know. So what pieces of information do we know from this statement? All right, what's my principal? All right, my principal is going to be $2,000, if I can write that. My principal is going to be $2,000. Okay? What other pieces of information do we know? What's that? We know the time. Okay, what's the time?
10 years.
All right, we want to know what it is if I leave it in there for 10 years. Okay? What else do we know? The rate. Okay? What's the rate? It's 5.5%. Now, whenever we're going to plug this into our formula, we never want to run it as 5.5%. We want to turn it into a decimal. So what's the decimal? Perfect. It's 0.055. Okay? So we always want to turn this into a decimal. Okay? So now that we have all of our pieces of information, right? I know that A, or the formula that we're going to use is A is equal to P to the RT. Okay? A is equal to P times E to the RT. Okay? So PERT. So plugging in the information that we know our amount is going to be, or if we deposit $2,000 at a rate of 0.055 times 10. Okay? Now, we're going to go ahead and enter this in our calculator. I'm going to show you how to do that using Desmos. Okay? So I'm going to pull up Desmos. So I'm going to type in 2,000 times, I'm going to type it in my calculator. And again, you can go to function and you can use this e to the x button, right? Or you can just type in the lowercase e and then go back and use the a to the b button if you feel more comfortable with that. to the, and then this is where we're going to get kind of weird. So I'm going to type in 0.055. Now instinctively you want to go times 10, but if you look at it, that's the 10, the Desmos automatically takes it out of the exponent. Okay? Exactly. You want to use parentheses instead. So 0.055 and then parentheses 10 and parentheses. And that'll give us our actual value. Okay? So that means that if we deposit $2,000 right, into a saving or into an account that gives or that has 5.5% interest compounded continuously, we leave it in there for 10 years, we'll have $3,466.51. Okay. 3,000. So our total amount is going to be, about $3,466.51. So now we're going to do number 2. And so we want to know how, so we suppose you invest $7,500 at an annual interest rate of 7% compounded continuously. We want to know 2 parts. One is how much will you have in the account in 10 years? And 2, when will I be able to save up and get $20,000? Okay? That's a pretty reasonable scenario because usually if you're depositing into a savings account, you're trying to save up a certain amount of money, right? So you want to figure, if I leave this in here, how long will it take to get to that point? Okay. So let's break it up first before we approach A and B. Let's talk about, okay, what do we know? What are some things that we know? Yes. All right. What's the rate? 0.007. 0.007. Yeah. 10. It's 0.07. Okay. 0.07. Okay. 0.07. What else do we know?
10 years.
Well, that's per part A. Let's just talk about what we know in general.
Oh, the principal is 7,500.
7,500. Yep. So my principal is 7,500. Okay. Now for part A, so that's all we know, and we know it's compounding continuously. Okay. So for part A, I know that I'm my T. All right, we want to know what happens if I leave it in there for 10 years. Okay. So again, since it's compounded continuously, using A is equal to P times E to the RT gives me A is equal to 7,500 times E to the 0.07 times 10. Okay? Which means I'll approximately have how much in my account? Who can tell me? $15,103.15. Okay, so that's great that after 10 years I'll have $15,000. If you look at it, so if we look at example 1 and example 2, example 1 had a slightly less interest rate, and I deposited a lot less money. In example 2, right, I didn't quite double my money after 10 years. But in example 1 I didn't. In example 2, I over doubled in the exact same amount of time. Okay? So again, those are the kind of things you want to think about if you're depositing money and what your interest rates are. Okay? When you're looking at savings accounts or when you're looking at loans and things like that. Okay? All right. So now we want to talk about B. Okay? So B, the information that we know is that A is equal to 20,000. Okay, so we want to figure out how long it's going to take for me to reach 20,000. So when I plug this in, I get 20,000 is equal to 7,500 times e to the 0.07 times t. Okay? So again, this is a problem different than what we've seen before because we're trying to solve for an exponent. Okay? So how we're going to do this first step is going to be just like we would normally. So I want to kind of isolate those things. So I'm going to take both sides and I'm divided by 7,500. And I should get about 2.67, roughly. And that's equal to e to the 0.07. Sorry, and I put parentheses. Apologize. Times time. Okay. So now, we will eventually learn how to solve a problem like this more accurately. But for now, what we're going to do is we're going to essentially guess and check. Okay? So what I'm going to do is I'm looking for e to 0.07 times some value equal to 2.67. Okay? So on my calculator, I'm going to go, okay, e, if it'll let me type, e to the 0.07 times what value is looking for, and I'm looking for 2.67. So if I think about it, I know it's not 10 years, because after 10 years I get 15,000. Okay? So let's just try something a little bit bigger. Let's what happens after 20 years? Okay? Well, after 20 years, it's 4.05, okay? Which is too much, okay? So obviously my number of years is somewhere between 10 years and 20 years, okay? So let's split the difference and let's go, okay, what happens after 15 years? Well, after 15 years, it's about 2.86, okay? Closer, much closer, but not quite, okay? So I know it's somewhere between 10 and 15 years. So let's just try 13. 2.48. Much closer, still close, right? But not quite. So now we know our range is somewhere between 13 and 15.
14.
There it is. That's right. So I plug in 14, I get about 2.66 or somewhere relatively close. Now again, this isn't precise, but it's close. So barring the how many months and how many days, we're not going to worry about that. Right? So we're just going to say, okay, that means after 14 years we should have that amount of money. So my approximate value, my t in this case, right, is approximately 14 years. Okay? Again, we'll learn how to find that more specifically either next week or the week after. Okay? But for now, we're just kind of doing guess and check. All right, do I have any questions on this? Pretty straightforward. Okay? All right, so I'm going to go ahead and stop the video. Please go ahead and begin working on your assignment for today. I know there's not a ton of time left in class, but I want to give you at least about 10, 15 minutes to work on it. Okay? If you have any questions, please feel free to let me know.